Okay. Um, uh, oh, by the way, one thing about, all right, so hi, hello, hello. I think you guys have been doing great, by the way. I think really honestly, I think things are picking up. I think you might be feeling it, whether or not, wherever you are in the homework. I think in the class, been talking a lot with the Walters and stuff like this, so I know where you are in lab and things. I think we are where we should be with the material, but better than that, whatever material we've been doing or we are doing, when I feel like I feel like you guys do understand what we're doing. And I don't feel like we move on until you do, but I don't think that's been slowing us down lately. Don't. So that's good. And it is true. I'm just going to remind you, it is true that we're going to have an exam a week from this Monday. I'll be more formal about it. I know it's good for people to know. It's not this Monday, but it'll be a week. Am I saying that correctly? Yeah, right. It's not this Monday, but it's a week from this Monday, which means you will have a practice exam distributed to you first, then you'll get answers distributed to you. I believe you'll have the practice exam by this weekend, but but even if at worst it's at the end of the weekend, it'll still be a week ahead of the actual exam for sure. We'll talk about it and you'll have solutions. So most questions or anxieties or anything that anybody might have about what the exam would look like or what it would cover or how it's formatted, all of that will be the purpose of the practice exam, is to address all of that. And we don't try to shock, like the whole idea is that you can nail this exam as long as you really work through and take seriously the practice exam. It's not meant to be a trick. We're trying to give you the formula in advance to speak. But as a result, like I hope it doesn't cause too much stress and I don't want it to infect us too much right now. Whatever you've been doing in class, please just keep doing. And we're really going to move forward with the material today, like in a big way. And you're going to start seeing how these labs are hopefully really connect because you all just added 3 vectors 2 days ago. And that's actually an accomplishment. I should stop and say, like, we all just slogged through the addition of 3 separate arbitrary vectors. That is just long and annoying enough to everybody. Like, let's be clear. I don't think it wasn't fun to do that for anybody. It's not interesting. It's not like that's why I live for physics, but it is just comprehensive and hard and long enough to add 3 vectors that honestly, most people will skip it. Like they sort of will never put themselves through that. And then they're always shaky with vectors as a result. But to actually go through and add 3 as successfully as you guys did, and I really feel like, I mean, obviously some people are louder than others, but I feel like at the end, I was getting messages in the chat and stuff. And again, if you still don't get it, that's okay too. But I do feel like you guys actually know what it means to add 3 vectors together, which in my mind means, what you're going to see today, it means that you really have the power of adding any kind of vectors, even more abstract vectors together in more abstract situations, and situations that mean more about science and physics. That's where we're going today. In other words, today we're going to start adding velocity vectors. The operation will be exactly the same. Like as long as you trust that you get how to do components and do SOHCAHTOA and Pythagorean theorem, as long as you get that, we're just going to keep doing that the rest of our lives as the way of adding vectors. But what's going to start happening now is that the vectors we're adding will have physical meaning that makes the whole addition much more, adds more choices and significance and difficulty to the problems. So just as like a warning, what we're going to today is the addition of velocity vectors. I'm going to give you a problem just as usual. We'll talk it through, blah, blah, and it will be on the exam, and like nothing will be nothing on the exam that you won't have seen before the exam. And everything from the exam is from all these notes. It's not from the textbook or anything. And sorry, one last thing about that. When you start going to prepare, again, we will give you a practice exam, and we will tell you that what you need to just live and breathe by is that practice exam. That it would be, as long as you understood it, then any other textbook or any other thing was just a means to help you get to it. As long as you understand the practice exam, you'll be set, okay? But when you're trying to understand it and understand this material, say you missed a class or something went too fast, if you're taking advantage of all of any of these YouTube videos, like where I post the class, and I kind of hope you are, only because I think it's because of them that some people don't really want to talk. So if you ever look at any of these YouTube videos to remind yourself of some material, I just discovered one thing that's sort of worth it, like, because of course nobody really wants to watch them, least of all me. But if you're like scrolling through one to just like see what I did or what we did in class or how to do something, which is the way to use them. If you're just like scrolling through them to find something like you would a book, you can't, I realized you probably all know this, but you can turn on subtitles. It really helps. And that way you really don't have to listen. You really can have it just on in the background just to find something, but you can turn on subtitles for but they don't automatically stay on, but you can turn them on for any one of these videos and then really just exploit it and use it for what you need. And then you can also find out how many times I say stupid things and every 5 minutes. But I think it'll be useful before the exam. But anyway, here's the situation for today that we're going to spell out now. Is almost this. Hold on, I'm going to modify this. Please write this down, but I'm going to modify this somewhat. Sorry. Okay. As illegible as this is, and as usual, I will rewrite this and try to diagram it for you. But here's the situation that I do want everybody to write down their own way or to picture now. Okay. It's a new vector situation, and it's going to involve the addition of vectors, just like 2 days ago, but it's now going to involve velocity vectors. So here's the situation. Imagine that you are walking along the sidewalk. You're walking, no tricks, you're walking purely horizontally, and you're walking east, which we can easily depict as right on the page. Okay, so you're walking east, and let's even say a constant velocity. In truth, it doesn't even really matter because we could just like analyze one moment of your motion, but in general, you're walking at a constant velocity, horizontal velocity of 2 meters per second relative to the ground. Remember, all velocities are relations between objects. Like you're going 2 meters per second past the ground to the east. That means the ground would look up and see you going 2 meters per second to the west, right? It also means that since the ground is going 65,000 miles an hour relative to the sun, that maybe you're going 65,002 miles like relative to the sun, right? Just to remind you that all velocities are meaningful only as relations, but the relation between you and the ground is you're walking horizontally 2 meters, and every second you're advancing 2 meters along the ground, like no tricks. But now, rain is falling down. And what I'm ultimately going to ask you, the question, you'll see that question mark there. What I ultimately do want to know about this problem, I'm ultimately going to ask you at what speed the rain is falling to the ground. Like the speed of you is 2 meters per second. What we're ultimately looking for in this problem is what's the speed of the rain. But I'm giving you one other fact, and you need at least one other fact to get that. And the one other fact I'm giving you is imagine that you're holding your umbrella. Hello. You're holding your umbrella successfully at an angle of like 68 degrees above the horizontal. Again, you should try to draw that first yourself to make sense of what I'm saying. But then of course I will also draw it to help you make sense. But the fact is, first of all, you've got this rain that's coming down at some unknown velocity relative to the ground. We've got you that's walking at a known velocity relative to the ground. You're walking to the east, the rain is falling down, okay? And by the way, you know, east-west is one axis, so we can call east positive if we like and say that anything going west is negative, and up-down is another axis, and we make a positive designation, a positive-negative designation there. And I'm gonna, in my mind, for what it's worth, I'm going to think of down as positive because rain is falling down. And so far as I know, nothing is going up in this situation. So, but you can make any designation you want. But what we have is down is falling. Downward fall is happening while an eastward walk is happening. Sorry, just admitting people here. And one of the numbers we know, and we're looking for the other number, we know that you're walking at 2. I want to know how fast the rain is moving, but of course the rain could be moving at any speed, except that it happens that you're holding your umbrella and it's keeping you dry. Like it's actually working. It's, in other words, let's assume it's matching the angle of the rain, your umbrella, it's blocking the rain as you want it to do. Why am I over talking this? And let's assume that, as is always happens in real life, like you just instinctively knew to, like, I think we all do know this. Like if you're just standing around and it's raining, you stand with your umbrella like this. If you start walking from one place to another, you may or may never have thought this through. And many people have, and many people, you may or may not have thought this through, but when you're walking, or if you start walking in the rain, instinctively, people do tend to start angling their umbrellas down. And if you're really walking in the rain, or if there's like super wind and the rain is like really going like this, or like you're in a vehicle or something, you may or may not have noticed that intuitively what people do is start angling their umbrellas more and more. The faster they're going, the more they angle them horizontally. And it's a totally correct thing to do. And in fact, if you don't do it, you get wet. Right now, no one's thinking through the physics necessarily, but what I am saying here is there's totally physics behind that we can analyze. So let's analyze it just the way, as if it were real life. Like there you are in the rain is coming down at some unknown speed. You know more or less the speed that you're walking, and you find yourself just instinctively holding the umbrella at 68 degrees. And it's like, okay, because you have a protractor with you too, because you're a loser. Because you're me. If these are the facts, if you know that your umbrella is at 68 degrees and you know that you're going at like 2, I claim that from that you can figure out how fast the rain must be going relative to ground, how fast the rain is vertically going relative to the ground, like relative to the ground. That's my question to everybody. That's what I want to know. I will rephrase it. I will start drawing it. But the question is, or the givens are 2 and 68 degrees. The question is, what's the velocity of the rain? Assuming it's coming straight down relative to the ground. I want to know the velocity of the rain. And that's what I want to know. So I'll shut up. So anything I do now, hopefully you've copied this down or you're thinking about it. And again, at any time, in the chat or publicly, you can say an answer. You can just say, I think I have an answer. You could say, I have a question. You could say, I'm stuck at this step, anything. But what I'm going to start writing is I'm just going to rephrase the problem more clearly. I'm not changing it. So hopefully you got it, but the next page will just make it more clear. Okay, looking in the chat. Wow. Wow. Huh. Okay. By the way, here's an opportunity for 50 points or whatever. Anybody who, either by show of electronic hands or in the chat or whatever, could anybody who actually understands what the question is, like what it is that they're supposed to be doing right now, even if they're not doing it. If you understand what you're supposed to be doing right now, what I'm asking, give me any kind of signal at all, electronic hand, thumbs up, or something in the chat, whatever, and you can count it for 50 points, literally. I just want to see. Thank you. Awesome. Thank you. I see. That's helpful. Okay. That's very helpful. It really is helpful because I'm going to take that to mean, and again, I mean this in a nice way, not, oh, wait, oh, yeah, yeah, okay. Right, so I asked that because as long as everybody's saying they do understand the question, when there's silence, like silence can be golden, right? Like if you all understand the question and there's silence, it could very well mean that a lot of you are actually really thinking and doing something, which is the best possible thing we could do with our time, right? It's better than me talking. What I'm here to do is like show everybody how to think on their own about physics. But if you all understand the question and you're all being quiet because you're all thinking, great, right? But if it's actually because like no one's doing anything I need to know, so it's very helpful to know. Now someone in the chat just, so I don't want to give hints when people don't want hints or whatever, but I think someone is asking for, right, okay. No, and again, anybody who put in the chat, I do understand the question or raise your hand, please, you can get 50 points for that. It's really helpful to me. And now for some people that was all of a sudden an opportunity to remind them that they want a hint or something, and that's fair. Yes, I'm gonna start writing hints that anybody who's thinking anything, they should ignore my hints until they're stuck, for real. They'll be more meaningful if you look at them once you're stuck. But I'm gonna start writing some stuff. You still can contribute or whatever, and I don't think it's gonna give it away. But yeah, I'm gonna start writing hints. But also I feel like I can now erase this page. I mean, if everybody understands the question, I'm gonna start setting it up the way I would, which will be hints, I think. But what we are solving for is we're solving for a velocity. Specifically, we're solving for the magnitude of a velocity vector. We are solving for a speed. Like the kind of answer we're all looking for here is a number that will be of meters per second and will represent how fast the rain is coming down, like relative to the ground. That's what we're looking for. And we're going to do it through treating velocity as a vector, as an arrow. That's what I'm going to do. So that's what I'm going to write down. But again, you can stop me at any time or whatever. Oh, sorry. My bad. Oh, okay. So I'm looking in the chat. But for anybody, what I just drew is not a giveaway at all, but it is a vector representation of the situation we have. Just so in effect, I believe I've given you two vectors here, and I'm looking for a third. And I'm labeling the vectors in kind of an exotic way, but well, and I know there's things in the chat. I'm going to look in the chat in 1 second. Sorry, but just to be as clear as I can. And you, of course, nobody has to do it exactly my way, but there is something to what I'm doing. Okay, hang on. So I am using U to stand for you or the umbrella, whatever, same thing. You're holding the umbrella. G stands for ground, R stands for rain. And I'm using those subscripts that way for what it's worth. And I also want to just make clear, and I'm about to look in the chat, but just note, and you can ignore what I'm doing if you're already doing something, but if you're using what I'm doing at all, notice I'm saying I gave you a vector that represents the velocity of what you're doing relative to the ground. And then I said something about, like that one I gave you speed 2 and direction due east. It's like 2 at 0 degrees if you like. The other vector, I gave you its direction, 68 degrees. I did not give you its length. Like, I just want to be clear. It's not a given what the length of that second vector is. It's not told to you, but also just to be clear, that's not what I'm asking for. You know, so it might muck you up. It might get in your way, and you might think you have to be clear. There's something in here that's both not being given and also not being asked for. You might think you might want to solve for it first in order to get the final thing you're looking for. That could be one way, or you might want to end run it. That could be another way, but just be clear. What you're solving for is this yellow thing. You're solving for a third vector, one that I'm telling you in advance that will be vertical. But I want to know its size. Okay, that's the situation. Now I'm going to look in the chat because I see there are things in the chat. Hold on a second. Great. Okay. Well, there's a lot in the chat, which is cool. And again, a lot of this in the chat could be public, but okay, I totally understand. Just give me a moment. Oh yeah, okay. So, oh my God, I just lost something. Sorry. Oh, okay, sorry. Ah. Ah. Yeah. Still going through, bear with me, I'm still going through this chat. Everything that's in the private chat is like so interesting and worth a response, and that's why I'm responding. It would be, it's amazing if this whole private chat were in public, it would be such a class. But so just bear with, but it is what it is. So just bear with me. Maybe it is what isn't. I don't know. And I can't. Okay. Yes, hang on. Almost there, everybody. I am going to, I think, okay. As of course, it's always true in every class that every single moment, every individual is not at the same place, and everybody has to kind of just be patient with everybody else's pace. But it's weird. It's true in all classes, but somehow I feel much more acutely aware of the weirdness here in these Zoom classes. Like I know at every single moment what I'm doing must be by definition not right for anybody exactly. What I'm getting at is I'm going to start now. Like I'm sure there's been too much silence now for some people who think they're done. I'm sure there's been too much silence now for some people who are stuck and waiting for something. And I'm also sure that what I'm about to say is going to be interfering with people's thoughts. But I've got to tell all you that I go through this private chat. Okay, what's going? And I might start. I've even now printed out these private chat logs for myself. I mean, they're private, so I'm not distributing them. But what's going on in these private chats is so awesome and so class worthy. Like every individual conversation that people are having with me is so clearly them advancing along the physics. And to be honest, why I get excited about the private chat, I got to tell all of you is everything I'm not blowing smoke up you guys when I say you're saying right things and getting things right, but you're also, the first things you say are wrong enough or not known enough that I know I'm showing you something new. Like I know you don't know it right away now from how honest everybody's being in the private chat. So it's much easier for me to make sure that everybody's sort of getting their money's worth through all these private chat conversations that are happening, except that they're all private, right? So what I just want to say is, please, I think the ideal would be if all of you would really feel the confidence to go public with your private stuff. Most of it like really deserves to go public, but I totally understand why you're not. And I will say, even I have to keep saying I'm giving the points for when it's public. I can't give direct points for what's in the private. Even if you want to use the private to confirm something with me and then you feel okay and then you go public and I give you the points for that, that's fine. I can't literally give the points for the private because it is sort of slower, right? It's not efficient for me to just keep having all these private conversations with everybody, but I don't want you to stop doing it at all. If in the end, if this is the way everybody's comfortable doing it, it's just like checking with me privately. And if everybody's willing to wait for everybody else, then what you're doing is so good. I don't want it to stop. If it is a choice between private or nothing, do it in the private. And you will end up getting the points and all that one way or the other, believe me. Like even if you will, and you'll rock the class. It's just, I think as we get more confident, we should go a little bit more public just to make things go faster. And also, if privately anybody wants to tell me, if anybody of you is like, look, it's all because of the stupid recordings, Yaverbaum, we would all go fully public if you'd stop recording this stuff and posting. I would listen to, I then have to make a decision. But if that's what it is, anyway, I'm just trying to say, I wish you could all see what's happening in the private chat because it is, everybody is clearly learning there and impressing me with the good stuff. So again, just bear with me that I'm taking a while to read it and respond and all that. I'm now going to go over the problem, but now I really know what the issues are of the problem. Okay, cool. Oh, wait, okay, I'm gonna start going over it in a second. What time do we have? Yeah, I'm gonna start going over it in a second, and I'm gonna know going over it. I'm gonna know what some people know, what they don't, and I'm gonna know, where it's worth spending your time. I know no one automatically knew the answer to this just by looking at it. But now, did someone say bless? That's awesome. All right, wait, let me. Okay, so I'm just going to catch up for a second. Oh, oh, now people are going public too. Okay. Ah, yeah, yeah. Oh, cool. Okay. Whoa, whoa. Wait, no, why is that my bad? No, she's right. Oh, no, good. Oh, wow. Now you're watching me have a conversation with myself. But now I'm reading the public, what you're all reading. Oh, whoa. Okay. Yes. Okay. So first of all, the ultimate answer to this question is indeed 4.95, like approximately 4.95 meters per second. I'm going to write, the answer is like 4.95 meters per second. It is approximate because there are like irrational numbers involved where we're chopping digits off the calculator. So it's approximate in the sense that it's really 4.95 something, something, something. But it's not approximate like I'm waving my hands like it's like rough. No, 4.95 is the answer, and it is meters per second, because what the question is asking is how fast is the rain falling relative to the ground. So before I am going to do it, but I totally do agree, yes, that is the answer. And some of us may feel more confident of it than others or see why. But yeah. Whoa, hello. Now, I'm going to do it, but let's just be clear. Like, this was a problem that asked for some kind of vector quantity. We were asking what the velocity of like something is. So our answer has to be a vector. That is, it has to be representable by an arrow with a particular size in a particular direction. And it has to have direction, right? So our answer is, and it has to have units because it's science. So our answer is 4.95 in the downward direction. It happens that the downward part of our answer, I already told you, like I said, the rain falls straight down relative to the ground. So what is its magnitude? Okay, but the whole vector is 4.95 straight down, and it's 4.95 meters per second. That is actually important. Hold on. That is a really important thing. I got a lot of questions in the private chat about this, and then some things in the public chat at the end. This is a very slippery business now. Now, we are talking about velocities. You're going to see that I'm going to draw arrows on a page and put the arrows together just as though they were displacements. But this is the power of vectors, that once we believe in the vector arrow, it can represent all kinds of different things. And in this case, these arrows, we're going to treat them just like we treated the displacement arrows the other day. But what they mean and what they represent are velocities. So in other words, that downward arrow right there, that's not a length. We're using its length to represent a speed. If that arrow were longer, it would mean that rain is falling faster. It wouldn't mean anything about how far the rain had gotten. Like, more specifically, this arrow is supposed to represent like how fast and in what direction rain is going at a certain point in space and time. And that point is the tail of the arrow. That's what's like, the whole arrow is big because it's representing a big number, but it's representing how fast something's moving right at that point, right at that moment, at that location, which is the tip. So hold on. So it's like, in other words, it's an instantaneous velocity that's being represented by that arrow. I may have said that the thing has a constant velocity, meaning every single instant is the same. But what we're using when we draw these arrows, we're picturing one instant in time, one place in space, and saying, okay, right then we're picturing something falling really fast. If it were falling slower, we would draw a shorter arrow. If it were falling even faster, we draw a bigger arrow. Okay, so far that's what we're saying. And so anything we're going to do with these arrows, if I'm going to add this arrow to any other arrow, the other arrow better also be a velocity arrow. Like I can add velocities to velocities, but I can't add a velocity to a distance. And whatever answer I get is going to be a velocity. So everything is going to be in meters per second. And here I'm going to take a slight risk. I want to really praise somebody. I think it was really smart and gutsy and attentive and worthy of 50 points, definitely, that Jamie, whose name I'm probably mispronouncing, so please tell me, but Jamie mentioned like you can change a velocity into a displacement or a measurement of length by using the average velocity equation. I think that's great, and that shows like connecting the material and everything, and it's totally true. I wouldn't do it here because, so that's, I'm taking a risk, like saying a slight critique here, but I wouldn't actually do that here because all the information being given is in velocity units, and all the information being asked about is also velocity units. So we're going to stay in velocity. I don't even want to translate to displacements. I could use that equation to do that, except actually, honestly, I also don't know anything about time. No one's told me anything about time here. So it would actually be difficult to convert these things into displacements. I'm just thinking of them as rates right now that I'm going to add together and get some other rate. But where everybody's right, definitely including Jamie, if I'm saying it right, and please tell me if I'm saying it wrong.
Sorry, it's Jamie.
Oh, I'm sorry, Jamie. Okay, Jamie, what she raises in the public chat is something also two people asked me in the private chat. Like the reason that it's very tempting to want to change these into meters or think of these as meters is because we are going to represent these quantities with arrows that have certain distance lengths. And what we are going to do is we're going to manipulate these arrows by the exact same rules and with the exact same logic that we manipulated displacement arrows 2 days ago and last week. Like in every way, we're going to treat these velocities as though they were displacements, but we're going to the whole while understand that they are velocities. So where I'm going with this is this. I'm saying we're given this vector. We are also given this other vector, right? We're given, oh, I'm sorry, no, we're not given, that's what we solved for. So like, how did I get it? How did I get it? Okay. Or how did, a lot of people got it, but I'm just now doing it my way. What time is it? Okay. So let's go back to the given. So this is, so how I got it was or how they got it is we're going to add velocity vectors together, just like we did Monday and Wednesday, and come up with a new velocity vector, like the sum of two, I mean, that just like we did yesterday, we added displacement vectors together to get a final displacement vector. That's what we're going to do here with velocity vectors. We're just going to be careful about how to do it. So we had, so the givens, we had that. And then we had this. Okay, and what we're trying to find some third arrow. Now, one thing I can do that I'm going to do, I'm trying to find a vertical arrow. Even if I'm not exactly sure why, I might do what a lot of you I think did correctly. Because you said, well, I don't know, like yesterday and the day before, we put arrows together tip to tail, and we got some arrow by doing that. And that's right. And that is what we did the last 2 days. And that's what I'm going to do right here. I am indeed going to start by putting these two arrows tip to tail. Sorry. I'm going to give myself more room. Sorry. Okay, I just put those arrows tip to tail, and remember, when you put two arrows tip to tail, then you are representing addition of those two arrows, and the sum of those two arrows is supposed to be the arrow that points from the original tail to the final tip, right? In other words, according to this picture that I just drew, this vertical arrow equals the sum of those two arrows, right? I'm not saying it's the only way in the world to add things or whatever, but just like yesterday and the day before, like if you walk north and then you walk northeast, and we asked ourselves, well, how far did you get overall? Well, we added north to northeast by placing the arrows tip to tail. And we said this, when we said we added them, we solve for the final arrow. In other words, I mean, it's so obvious in a way when you're talking about displacements that it seems not worth saying, but it really is not obvious here, and it is worth saying. I'm saying, remember, when we talk about putting arrows tip to tail, what we mean is you take two arrows, put them tip to tail, and that forms 2/3 of a triangle. The third, the last arrow that points from the original tail to the final tip, from the initial position to the final position, or the initial, starting to the final. Yes, it's totally. Right. Yes. So I'm ultimately getting at the Pythagorean theorem, yes. But I'm saying even if, but I guess what I'm really saying, in this case, yes, we are going to use the Pythagorean theorem. But I'm saying even if two vectors together form a triangle which isn't a right triangle, okay? And this is where it gets a little bit tricky from 2 days ago, but any two arrows that you put together, even if they don't make one big right triangle, even if they just make a crazy triangle where you have to do more work to solve the whole thing, still nonetheless, that third side, that third side represents an arrow going from the original tail all the way to the final tip, and therefore that third side is the sum of the other two. That's what we believed 2 days ago, and I'm saying that's what we're going to keep believing about, even about velocities, whether or not the triangles are right. And yes, again, the Pythagorean theorem will be involved in all the right triangles. But even if your triangle isn't right, so I'm saying, if I place this diagonal arrow, VR, this downward pointing arrow, the yellow, tip to tail with the horizontal arrow, and then if I complete that triangle with a vertical downward pointing arrow, I actually do have here a triangle that coherently does represent this problem. That is to say, according to just this triangle, the hypotenuse, necessarily this is a right angle. Now, so this is where the Pythagorean thing comes in. I'm saying that if you don't just draw this as a raw geometric triangle with just sides, but you actually put in the arrowheads, the tips and the tails, then you have this downward arrow plus this horizontal arrow apparently equals the vertical arrow. Like if I can get that vertical side of this triangle, evidently I actually am getting the sum of those two. And perhaps I am, in fact, getting the answer that this question is looking for. I think I am. In fact, I'll be getting the rain falling down to the ground. In other words, and this is where I agree with like a lot of people, what they did in the private chat, whether they felt confident about it or not. I'm now going to blow up. I'm definitely saying the triangle to work with here for sure. Whoop, I keep doing the triangle to work with here for sure is and very specific, and a couple of people put drawings in the private chat and really good drawings. Like what I'm trying to emphasize here is, yes, there's triangle. Yes, we're doing the math of triangles. And yes, we need to know the math of triangles. But the physics part is the arrowheads. Like the triangles really can only do so much without arrowheads. Forcing yourself to think through the arrowheads does make it harder to think through, but it makes it more powerful. And a couple of people did submit diagrams to me, like actually had the arrowheads, which are great. And I almost do want to share them, but I'm not going to at the moment. But I'm saying, take this very literally. We are really saying in vector language, down and to the left plus pure right equals down. Like that's what we're saying. This being definitely a right triangle. And what we're saying is, okay, if this is given, and this is given, this side, this lower side of the triangle is a side of a triangle. Like it's long, it's 2 units long. It's, you know, it's shorter than the hypotenuse for sure, which is some number of units longer. They are units of length on my graph paper here, but they represent quantities in space and time. Like that base of that triangle is the velocity, the instantaneous velocity, 2 meters per second. But I believe that I can use my knowledge of triangles to get how many meters per second that other side is. I'm looking for this. I remember, sorry. Right. I'm sadly going to go. Sorry to do this. Wait, am I not doing? Did I get? Wait. Sorry. Yeah. Okay. Sorry. Right. Back there for a second. Okay. So one thing is that is how to get the. I have more to say about this. Surprise, surprise, and I want to generalize this to like a bigger point. But I am saying the answer is like approximate is 4.95. I guess we already said that. The answer is like 4.9. No. I'm sorry. Yes, but this is drawn. I'm sorry. The answer is what I'm saying. The answer is, but I see this is very deceptive. I don't mean to imply that the hypotenuse is that size. Sorry, just because of where I'm writing it, it looks totally. I am saying that the answer is like 4.95, by which I mean, and this is very important, I mean this answer that we're looking for, the vertical side of the triangle. This, if you put into, like that is opposite the angle. And I'm saying tangent equals opposite over adjacent. So, and I'm solving for the opposite. So I'm saying opposite equals adjacent times tangent, right? Just to be super clear. So I'm saying that the answer is what you all think it is, I think. I am saying 4.95, but I just looked at my own picture and realized how deceptive that was. I'm saying that that side of the triangle is 4.95, like just like a little bit below 5. Therefore, to be clear, you can totally do the Pythagorean theorem, or you can do cosine or sine or something, and you can solve for this other side. Let's make this super clear. You can solve for this other side. And what you'll get is, I think, like 5.4 or something. Well, I'll check right now. I think you get like 5.4. You get the square root of 28, yeah, which is 5.3, sorry, okay. So for this other side, let's make this very clear. You would get like 5.33, which means that any of you, and there were some, anybody who got that as an answer is doing something so deeply right, especially if they had a triangle that looks like this. And honestly, at least one person did. There's at least one person who had a triangle that looked like this, which I think is a hard triangle to draw. Like anybody can draw the triangle. But if you actually take the time to put the arrowheads in, which will ultimately make all the difference in physics understanding, I got this triangle for some people. Now, if in the worst case scenario, if they accidentally wrote down that their answer was this thing, that's a minor confusion, right? I can tell they've done everything right, and then they're just like plucking the wrong answer accidentally at the last moment, you like forgetting what the question is or whatever. The question is, what does VRG equal? And the answer is 4.95. This hypotenuse is totally meaningful, excuse me. If you got that the hypotenuse is 5.33, you're doing everything right, and you're right, and your understanding of the whole world is right. If you got that the hypotenuse is 5.33, you who all of you are, as long as you understand that 5.33 happens not to be what the question's asking. What does the 5.33 actually mean? The 5.3, if we were to do it in subscripts, the 5.33 means something in real life. It's not VUG, and it's not VRG, it's V something something. And I'm gonna ask all you that, anybody who wants to in the chat or vocally, like if we're using these subscripts, and this is where the subscripts start really meaning something. Like again, I'm saying geometrically, mathematically, the answer to this question is 4.95 meters per second. But what it means, how we got it, what is going on here, we'll really be able to know once we understand these subscripts. I'm saying that what was given in the problem was the velocity of u relative to the ground as 2 meters per second. And what you found was the velocity of the rain relative to the ground. What does this 5.33 represent? I'm asking anybody or everybody. It's V something something. It's not RG. It's not UG. Like, what is this 5.33? And again, if you even just said, I understand the question or I know the question, that'd be helpful too. But I'm literally asking, so maybe I need a new picture. Like, let me say it one other way. This 5.33 is kind of the hook of the problem. Oh, Ardell, I'm sorry, Ardell.
Oh, I was just asking if that represents the velocity of the rain relative to the umbrella.
Yes, we're done forever. Sorry, no, yes. And I know I always get over, okay, there's no drama. Everybody's fine. Everybody remain calm. But yes, can I just say yes? Oh, I'm looking in the chat and other people may have said it also in their way. Hold on. But yes, can I say yeah? Oh. Yes. And you can put it that way too, like in the chat. Yes, the way, yeah, the way when you put in the chat is a different way to put it. It's totally right. And it's not an accident that, like, right, I'm using U to stand for umbrella or U, and they are both the same. Like Ardell said in terms of the umbrella, and when you saying it in terms of U, and that's both correct because you and the umbrella, you're not the same object. I know, like you're much better looking than an umbrella, whoever you are, unless it's a really good looking umbrella. I'm just kidding. But like, obviously you're not an umbrella, but you are in the same reference frame as the umbrella. Like physics wise, you and the umbrella are going same speed and same direction, presumably according to this problem. You and the umbrella are seeing the world the same way. Like the earth is going past you both the same way. So whether and this is also why I like it when more than one person says the answer, like Ardell's way, Wendy's way, both right. And I'm gonna write down, like that missing subscripts there, that side that I didn't give you and I wasn't asking for. So it might have looked in the way, or it might have looked like you had to get it first. And by the way, some of you could have gotten that side first and then done SOHCAHTOA. It might make you more comfortable, totally fine. As long as you keep in perspective what the question is, that side that I didn't ask for and you didn't actually receive, that is, as Ardell and when you said, that's the velocity of the rain relative to you or to the umbrella. Now, why am I so excited about that? Because what I'm trying to say now here is, okay, what we have been learning for a couple of days is how to add vectors as like a tool. And we learned it with displacement vectors. A displacement vector is just a short version of the real thing. Like it's an arrow that represents a distance. And the arrow itself, it's an arrow that represents a length. And the arrow has a little length, which represents a bigger length. So the displacement vectors are just like scaled down versions of reality. But now we're going to take the technique of displacement vectors, like this idea that when you add them tip to tail, you get stuff. And we're going to apply it to velocities, where we're apparently now going to be able to add velocities. And what this picture here is saying to me is that we can add velocities as though they were just distances, but we can only add them if we are very careful to honor their relative quality. Like if you look at this diagram, I'm going to blow it up again in a second. This diagram says that one velocity plus another can equal a third. But the two velocities being added are very particular. Notice that what's happening in this diagram is it's saying the velocity of the rain relative to you plus the velocity of you relative to the ground gives us the velocity of the rain relative to the ground. It almost sounds like it does make perfect sense maybe once you hear it. And like it does, there's no trick, it's right. It almost sounds like it makes perfect sense once you hear it, but so much sense that you might not think of the millions of other possible ways that aren't right, that people, in other words, what this is saying, I'm gonna write it down in a second, but it's saying we can add velocities and get meaningful answers, but not just any old random velocities. If a baseball flies past, if a baseball flies past me in the room at 3 miles an hour, and at the same time a watermelon flies past me in the room at 5 miles an hour, I got a baseball going 3 and a watermelon going 5. I can do the math and say 3 plus 5 is 8, but that doesn't mean anything in the physical world. Like there's no significance to the 8 number. It's not like that, it doesn't mean that since there's a baseball going 3 and a watermelon going 5, that in the room there's like 8 units of motion. That doesn't mean anything. Like the 8, like at all. Similarly, if I say there's rain going past me, if I say there's rain going past the ground and an umbrella going past the ground, there's nothing about those two numbers that can be added together to mean anything. But if I say that there's rain going past an umbrella and an umbrella going past the ground, then I can add those two together and get rain past the ground. But what we're saying, in other words here, we're still saying that to add vectors, you place them tip to tail. But now we're saying when they're velocity vectors, here's the ones that you're allowed to place tip to tail and what you get when you do. What we're saying is here, what we're saying. Well, yeah, so what I'm talking about here is so just to look at this board for a second, I'm saying, yes, when we place two vectors tip to tail, we add them. But what does it mean to add velocity vectors? It means to take advantage of their relative quality. It means to remember this. Okay, so this board is what, please do write this down. I believe we've said this before. In fact, we may have said it one too many times. We were discussing this stuff back in the early day of this class, when I'm sure everybody hated everybody, especially me. Like when we were talking about train of thought and planet Earth and stuff that didn't look like it was helping anybody with problem. I'm sure it was like what did it have to do with anything? And it wasn't helping anybody with problem solving. I know that. And it was like this abstract discussion of velocities. And remember, and I'm going to refer you back to it now. And I'll write the stuff again, but I do think you have it in your notes and in the videos. Like our big point then is Galileo's principle of relativity, GPR. Like it's really going to start mattering now in a big computational way. Our big point was, okay, and I'm looking at the time, I'm aware of the time. Galileo's principle of relativity in its first form, in form number 1, it's not written on the board here, I'm just reminding you, the original form of Galileo's principle of relativity is the laws of physics are the same at all constant velocities, in all unaccelerated reference frames, in all unaccelerated coordinate systems, however you want to put it. The laws of physics are the same from one velocity to another, was what we said. Then we said form number 2 was, well, therefore there's no experiment you could ever do to measure the actual absolute velocity of any one single object, because whatever experiment you ever do is going to, because the laws of physics are the same at all speeds, whatever, if you're trying to figure out what speed am I at? I'm on an airplane. Am I going past the trees am I going past the clouds, or the clouds just going past me and I haven't even taken off yet? Like how fast am I actually going? Not past something else, but is that thing going past me or am I going? And so you try to do an experiment to figure out what you're actually doing. But the laws are the same at every reference frame. So whatever experiment you do, at whatever speed you're going, the experiment's going to result the same. You drop something next to you, it's going to land on your foot. If you're in an airplane, no matter how fast, even if you're going 700 miles an hour, as long as it's constant, right? As long as it's constant, you could be going 700 miles an hour in a particular direction. And if you drop something, it just lands next to your feet, just as though you were standing still. Which means then to us, which meant then, and this does relate back to this, form number 3 says, well, so form number 2 says there's no experiment you can do to find out if you're actually moving or something else is actually moving. You can't. You'll always get the same experimental results, whatever speed you're going, because the laws are the same no matter what. So then our third form was, then in physics, all velocities then are relations. There's no such thing as the velocity of a thing in and of itself. That does not mean anything in physics because there's no experiment you could ever do to even find that out. And we are an experiment, we're a data-driven science. We are science. So what we said in form number 3 is all velocities are relations. The only meaning to any velocity is as a comparison between one object and another. You need 2 objects to have a velocity. And this all is going to bring us to these arrows now. Like the way to add velocity arrows is to recognize that each velocity arrow could only be written with 2 subscripts. you have to put the two subscripts. I mean, if you only have one subscript or you have no subscripts, it's not actually a velocity. A velocity is a relation between two objects, such that, now here I'm going to remind you, I think we've said this before, but I'm saying form number 4 of Galileo's principle. This is all coming from like believing that the earth could move without us feeling it. All of physics comes from, holy crap, I think the earth is moving, even though I can't feel it. Like, what does that mean? What it now means in the fourth form of that, where it starts getting mathematical, and here we are, finally we've arrived at a place that's very mathematical in this class, for good or for bad. According to Galileo, form number 4, okay, it has 3 subcases. This we've written before, but I'm writing it now specifically for these vectors. I'm saying from now on, if you draw V with an arrow over it, like V with an arrow over it means velocity, the vector, the magnitude, the direction, the arrow representation, like this means vector from now on. If we're dealing with the velocity vector, then first we have to realize that the velocity of any one object to itself, like, so let A, B, and C stand for arbitrary objects I've written up here. Like, let lowercase a, B, and C just stand for any 3 random objects, like you, a subway train, and a New York City street, or an orange, Earth, and the sun, whatever. Any 3 objects is what A, B, and C are. What we're saying is the velocity of one object relative to itself is always 0. No object ever has velocity relative to itself. No object has velocity by itself. To itself, an object is always not moving. Like my nose is always right in front of my eyes. Like, duh. So you need at least, I mean, duh, but not duh. So we're saying you need at least 2 objects to have a meaningful velocity at all. You need at least an A and a B. But then what happens if you just have those 2 objects? The velocity of A relative to B is perfectly symmetric with equal to the negative of the velocity of B relative to A, meaning if you see me zoom past you at 10 miles an hour heading east, then I see you zooming past me at 10 miles an hour to the west, right? Like, everybody knows that visually, but we're saying in physics, both visualizations are equally correct. If they're both legitimate data, like if I literally measure you going at 10 meters per second to the east, constant velocity, then you would measure me going 10 meters per second to the west relative to you. And neither one of our frames of reference is objectively correct. All velocities are relations, right? So velocity of me relative to you is always the opposite of the velocity of you relative to me. That's the situation we have if you have 2 objects under consideration. Now we get to where we are here in the class. And I know there's only like 2 minutes left. But once you have 3 objects, as we do in the case at hand, we have an umbrella, we have a rain, and we have a ground. 3 objects, right? Then we can add then it becomes meaningful to add velocities, but we add them in exactly this fashion. And here's the thing to write down, the key that you may have written before, but the way of solving this problem and where we're sort of going to end today is the truism for all time is whatever A, B, and C stand for, velocity of AC equals velocity of AB plus velocity of BC. This is very deep, actually. It seems obvious once we say, and hopefully it does seem reasonable once we say it's like the law of transitivity or whatever. But what this really is here, and we're going to end, I know what time, I think I know what time it is. Yeah, I think we got like a minute and a half, but this is where I want to end up. This is all an explanation of why the triangle actually makes sense and means something and works. And then we'll use it for other triangles. But I'm saying, picture that the 3 objects in question are like you, a subway, and New York City streets. Like this statement here, VAC equals VAB plus VBC, like this statement of how to put velocity vectors together, to add them tip to tail and what you're getting at the end, is what we always believe. I get on subways because I believe that I can go, I mean, I don't during the virus, but like outside the virus, why do I ever take a subway? Why do you ever take? Because I believe that I could have a velocity of me relative to the subway, which is 0. Like I can chill on the subway. Have the velocity of me relative to the subway is 0. The velocity of the subway relative to New York City streets is like 80 miles an hour. And I believe that me relative to the subway plus subway relative to streets equals me relative to streets. So I don't move at all relative to the subway, but I move relative to the streets at 80 miles an hour and I get home, right? It works more really, what I'm really believing psychologically is you're bringing this me at 80 miles an hour in the other direction because I'm just standing there while stuff, right? But we so believe this. What I'm here to say is like, you already knew this was true. But what's true that you already knew is that velocity adds like a vector. It really does, but just know this, right before we leave, because we're about to leave, I know. But the big truism, like if this triangle that we just did with umbrellas and everything actually works the way we think it does, the triangle that we drew, which I've lost now, but I had a second ago. If we believe that the triangle really works the way we're saying that it works even with negative signs, even when values aren't equal to 0, and even in all kinds of directions. In other words, I really believe, I really believe that if I walk up the down escalator in a mall, right? If the escalator is going down at 5 miles an hour relative to the mall, and I walk, if the escalator is going up at 5 miles an hour relative to the mall, and I walk down the escalator at negative 5 miles per hour relative to the escalator, then you can stand there in the mall and watch me, and I'll look like an idiot, like a cartoon character with my legs and arms flailing, but getting nowhere relative to the mall. Because my velocity relative to the escalator plus the escalator's velocity relative to the mall is my velocity relative to the mall, even including negative signs, even including cockamamie directions. Velocities add across frames of reference. You can't add this is the last thing I know at the top. You can't add the velocity of the baseball relative to the room plus the velocity of the watermelon relative to the room. That doesn't mean anything. You can add the baseball relative to the room plus the room relative to the ocean, and say the room is on a cruise ship, and you'll get the velocity of the baseball relative to the ocean. That's how velocities add. I could have sworn I had this written down. Oh yeah, what I'm saying right here. And notice, if you really take it seriously, then it means, oh, you can subtract from both sides. Sure, if you have two velocities in the same frame of reference, you can subtract them. Like velocity of the orange going through the room at 5 miles an hour, if there's a velocity of a tennis ball going only 2 miles an hour, oh, well then yeah, the orange is going 3 miles an hour faster than the tennis ball or whatever. Like you can subtract them if they're in the same frame of reference. But if you want to add velocities, they have to be in 2 different frames of reference. So, but the answer was right and everybody's right. And I know it's 1:30. So if that's okay for the moment, we'll leave it at that and we'll just keep going with this. But is that cool? Goodbye. Thank you. Or could I just get a goodbye or something? Just to, I don't even know if I've been heard for the last.
Bye.
Bye. Thank you very much. Okay. Bye. Thank you guys very much.